All right, so today we are going to be describing linear functions. And the first thing we're going to talk about is the domain and range. Okay, so we need to be able to determine the domain and range for any linear function that we work with or graph. Okay, and this is not just for now we're just basically graphing them. This is also for later when we start using like real world functions and we try to see what the domain and range are then. Okay, so first off, let's talk about what domain and range is. Okay, so the domain of a function the domain of a function is, and I need you to make sure you're emphasizing this, all of the x values of a function or a relation. Okay, and we're going to talk about how we write it because there are special ways to write it so that we don't have to keep just listing off numbers. Okay, so if the domain is all the x or the input values, and you can put that under there as well, just to remember that your x is your input. The range is all of the y or output values of a function or relation. And again, that comes more when we're starting to do like real world linear functions, sort of like how much money do you have to pay for phone service, or how much money do you have to pay for a car, all kinds of different things that we can do with linear functions in the real world. Okay, so the domain is all of the x values, the range is all of the y values. All right, so let's do a couple of practice ones so you can see how we write this. Okay, so I'm going to go ahead and just graph the function. So this should be a review already. You should have already been graphing linear functions before you start describing them. But as a quick review, we're going to start off at the y-intercept, which is the point 0, -4. And then our slope is 2 over 1. So rise 2 and run 1. So 0, -4, rise 2, run 1. Do this a few times. And then we're going to go ahead and connect the dots. And remember that you are putting arrows on the end of this. This line does keep going forever and ever, right? It does not stop unless, somehow you're, basically restricting what you're allowed to have. Okay, so the domain. Now, I could sit here and list off numbers, right? Obviously, for the x values, I have an x that is at the 0. I have an x value that's at 1, that's at 2, that's at 3, that's at 4. But because this line is connected, it means that I have all the decimals and fractions in between those as well. And I don't want to sit here and list off 1, 1.1, 1.2, even 1.01, all those different little numbers that are in between. Okay, so what's important to check is that at 0, I do have an actual number. I have x's that are positive on the right-hand side, right? I have points that are sitting at positive x numbers, and I have points that are sitting at negative x numbers. Okay, so remember that is the negative x, this is the positive x. So we have a shortcut way of writing this. Okay, so if I have all the positives and all the negatives, and I do have them all because that arrow means it keeps going, and I have 0, then I have a special way of writing it. And I can write it in words or I can write it in symbols, and I'm going to go ahead and give you both. Okay, so in words, what I have is called all real numbers. Okay, because all real numbers, if you remember back from Unit 1 when you were doing rational numbers, all real numbers means all the fractions, all the decimals, positive, negative, and 0. Okay, so all real numbers, and the symbol for that, or in what they call interval notation, is from -infinity to +infinity. Now we call it that because, again, do you see how the arrows are on the x and y axis too? That's negative x, and that is going to keep going. There's an arrow there forever and ever until it gets to -infinity, and it's just going to keep going and going and going forever. And the right side will keep going forever and ever, and it will go towards the positive side. So that would be +infinity. Okay, and then we have symbols for that. So your domain, all the x values that could possibly be in this function, is everything from negative infinity to positive infinity. And what that really means is that I can substitute any number that I want for this x, any real number. Positive, negative, fractions, decimals, zero. I can substitute any of those x values and I will actually get an answer. Okay. And as long as I'll actually get an answer for it, then I'm allowed to have that x value. So the range, same process, is going to keep going forever and ever down to the negative because of the arrow, and up to the y positive, again, because of the arrow. And again, I have a point that is sitting at a 0 for the y. Sorry, that's over here. So I have everything. So I have no what we call restrictions on the numbers that I am allowed to get. Okay, so I'm going to give you an example so you can see something that does actually have a restriction, what we call a restriction. Okay, so just so you can see the difference between something that does not have a restriction and something that does. All right. So if I were to put a function with a dot instead of an arrow, and let's make it go up to here, and then I'll make it go down and have an arrow on this side. Okay, so this has a restriction. Okay, so when we were to list the domain of this function, I am not going to get every possible negative number for x because the graph stops. Now, I will get all the positives because this side actually has an arrow on it. So the domain of this function would be from -8 to infinity. Okay, and if you want to know why there's a square parentheses, a bracket on this side, and a regular parentheses on this side, it's because -8 is an actual number that is in the graph, right? And infinity is not really a number, it's just a concept that we keep going and going forever and ever. So that would be the domain. The range, again, I am not going to get all my positive y's because it's going to stop here. Okay. So the highest I can go on my y values, 3, 4, 5, is 6. So my range would be from -infinity to 6. And the reason we write it that way is because we normally put the smallest number first. And -infinity is a lot smaller than +6. So see, that's a difference between a function that has a restriction, it can only go so far, and one like what we just did, where it's going to keep going forever and ever in both directions, up, down, left, and right. So let's try another linear one. All right, so again, this is just practice as far as we've already learned how to graph these. So the point that I start out is -1, +8. Okay, and my slope is -3/1. So I'm going to rise 3 down and run 1 from my starting point. So -1, 8. And then I go down 3 to the right 1, down 3 to the right 1. And again, draw my arrows on the end because the graph does keep going forever and ever in both directions. So same as the first one, what is going to be my domain and range? Can I put any number that I want for x? Am I going to get all these negative x's on the left, including all the fractions and decimals? Am I going to get all the positive x's on the right because of how it keeps going? And do I actually have a 0x? I do. So that means my domain, same as it was before, is all real numbers or from -infinity to +infinity. Same thing with the range. I can get all the positive y's over here, even though it's, the graph is flipped around, all the negative y's over here, and I do have a place where y is 0. So it is all real numbers. Okay. All right, so again, one more, just so we can make sure we're practicing all three forms of linear functions. Okay, so we're going to graph this. And if you remember, this is the one where you are going to find the x and the y intercepts. So the x-intercept is where y is equal to 0. So if I make y 0, then I have to divide 12 by 2 to solve. And then my y-intercept is where x is 0. And if I make the x 0, then I have to divide 12 by 3 to solve. So those are my 2 points, and I can also find my slope from that if I want to. 6 and 4. And if I wanted another point, then I could go down 4 and over 6 more. Now that's going to be off my graph, but I can do it if I wanted to make my graph nice and straight. Okay, connect dots, put your arrows. And as you can see, again, the domain and the range are both going to be all real numbers because there is nothing left out. There's no stopping place on my graph. It doesn't turn around and go the other way. There's no dots that are stopping points where I don't have an arrow going past them. So negative to positive infinity. Okay, so that is domain and range. So we have one more thing to talk about, and it is what we call end behavior. Okay, so the end behavior is very specific. It is where the ends of the graphs are going. Okay, the only thing on this is that there's a very specific way that you have to write it. Okay, so I'm going to show you a very specific way. Make sure you're copying this down. So what we say is the left side. So picture the left side of a graph, right? This is this left side already. Okay, so we already know that this is going to be negative infinity over here, right, for the x's, and this is going to be positive infinity over here for the x's. So the left side is always going to be x going towards negative infinity. And you can always make that a symbol as well as just negative infinity. Okay, and then y goes to. Now here's the thing. If the graph is pointed this way, right, as x is going towards negative infinity, as on the left-hand side, then y is going up. So it's going to positive infinity. But if the graph is going the other way, like this, then as x goes to the negative infinity, y is also going to go towards negative infinity. So you have two different possibilities. But the left side, x is always going to be negative infinity, and y is either going to go to positive infinity or negative infinity, depending on which way it's pointing. Okay, so on the right side, well, the right side for x is always positive infinity. So again, you can write it out, or you can use the symbol. Okay, so as x goes to positive infinity, again, if it's like this first example, it's going to point down, right? As x is going to the positive, y is going to go to the negative. If it's like the second example, as x is going towards the positive side, y is also going towards the positive. So you're going to need to make sure you're looking at your graph to see which one it's going to be. And we'll do a couple again, just as examples so that you can see how to write it. And I'll even show you the shortcut way to write it, which is kind of nice. All right, so again, practice. We always need to practice our graphing. That one has a y-intercept that we start at 0, 5, and a slope of 2 over 1, right? Rise over run. So 0, 5, slope of 2. Connect the dots. Okay, so left side, do the left side first. We know, okay, so it's x, and you can put this little arrow. It's actually pretty cool because that means it's going toward negative infinity, right? This is where x is going over here on the left side, always negative infinity. Where is the y pointing down to? Well, it's pointing down, which means as x goes to negative infinity, y goes to negative infinity. And again, that's the shortcut way to write it in symbols. You are welcome to write it out in words. There's nothing wrong with that. Okay, then on the right side, okay, so over here we know that this is the positive side, so it has to go to positive infinity. As x's are going toward positive infinity, right? That's where this is eventually going to go, positive infinity for x. It's also going toward positive infinity for y because it's pointed up. Okay, so as x goes to positive infinity, y goes to positive infinity. All right, so let's do an example of one that's pointing down so you can see the difference. Okay, so again, we're going to graph it using x and y intercepts. And when the x-intercept is when the y is 0. So if I make y 0, I have to divide 18 by 3. So that's 6, 0. And then the y-intercept is when x is 0. And if I make x 0, then I'm dividing 18 by 2 to solve. So that's going to be 9. Okay, so 6, 0, 9, 0. Ooh, that's not going to be a straight line, but that's okay. I'm sure yours will look much better. Okay, so same deal. Left side is always first. So as x is going to negative infinity, where is the y going? Well, the y on the left side is pointed up, so it's going to positive infinity. Okay, and then on the right side, as x goes towards positive infinity, right, because that's where it's pointing, is to the right. Well, the graph is pointing to the right for positive x and down for negative y. So y is going toward negative infinity. And that's it. You have just described the domain, the range, and the end behavior of all the basic linear functions that we are graphing right now.